Very similar calculations. Example 7. If we looked at f of xy equals to x, then can show that partial x equals 2 and partial x partial y equals 2. You guys fill in the blank for me. I hear a 1, I hear a 0. Correct. So what is, let's talk about notation a little bit. We can write partial f, partial x. We can also write f sub x. It's also partial x of f. These are notations I use for the partial derivative with respect to x. Okay? Partial f, partial y. We can also write as f sub y. And that could also be written as partial y of f. If you can do this once, you can do it more times. So like we could talk about partial squared f, partial x squared, and that would mean partial x of partial f partial x. And we also use the notation fxx for that. Or partial squared xf. This one's a little funny. If we have partial squared f, partial x, partial y, that is partial x of partial f, partial y. Which is partial x of f sub y. Which is technically fyx. So there is a little bit of a wrinkle here in that this notation and that notation are a little bit at odds. But the good news is, guys, we'll soon see that if you do x then the y derivative versus if you do y then the x derivative, you get the same answer. So like this notational subtlety actually never hurts you, because we have a general theorem that fxy is equal to fyx for pretty much any function that you're ever going to differentiate, unless you're a mathematician. And specifically trying to come up with a function where that doesn't work. But it's pretty hard to come up with one. Okay, more. Let's do more examples. So what are the properties of the partial derivative? I don't want to prove those today. I'll prove some of those tomorrow perhaps. But it should be somewhat evident from the definition that, well, you look at this, right? So, the partial derivatives enjoy same calculus as like ddx, right? Or ddt. With the wrinkle that we have to hold the other variable as constant. Okay? So let me do the calculation in example 5. Let's go back here again and do this example using our newfound ideas. Yep.
So I assume that means there's a partial integration?
A partial integration, eventually, something like that. But we don't, that doesn't, for whatever reason, that doesn't seem to have a agreed upon nomenclature. Like there's no, you won't see people writing integral partial. I do sometimes, but I guess I'm not a person. But, all right, so here's the deal. Partial x of 25xy. All right? Because we're holding y as a constant, we can pull it out of the differentiation and the 25 as well. So this is 25y times partial x, which is 25y. On the other hand, partial y of 25xy is equal to 25x times partial y, because we're holding x as a constant while we're taking the y derivative. Oh well, I tried. And so that is 25x. Let me put it in more the other language. So for f of xy equal to 25xy, we have f sub x at the point xy is equal to 25y. And we have f sub y at the point xy is equal to 25x. So f sub x at the point 1, 2 and f sub y at the point 1, 2, what are those equal to? 25 times 2, which is 50, and 25 times 1, which is 25, right? Which is what we worked out up here. All right. So just to circle, I wanted to make sure I leave you with the correct formula for for the calculating the directional derivative. And we're going to talk a lot more about directional derivatives in here. We're not done with that by any means. But if you put my, just to write my claim more systematically, let me do it over here. So actually, some people actually take the formula I'm about to write as a definition of the directional derivative. Technically speaking, that presupposes a certain niceness of the function that you're dealing with. So it's not really a very good definition from a mathematical perspective, but from a pragmatic perspective, it's a very good definition. So I'm going to call it a theorem, though, because for me, that's what it is. If f is a function of two variables, so we can write it this way: if f equals to f of xy. This kind of language is used in engineering a lot, right? That says it's a function of two variables. Has partial derivatives partial f, partial x, and partial f, partial y, which both exist at p naught, then the directional derivative in the u hat direction, well, let's say the AB direction of f at p naught is equal to a times partial f, my partials are degrading, partial f, partial x at the point p naught, plus b times partial f, partial x at the point p naught. So if u hat is equal to AB, and we define nabla of f equal to partial f, partial x, partial f, partial y, you're going to ask me again, this is nabla. Sometimes it's also read del, yeah.
We put plus b partial f. Is that?
Oh, thank you. Good grief. Yeah, that's a y. Sadness. Anyway. Then, with this notation, by the way, this is the so-called gradient vector field. Of f. Well, check this out. We can write the directional derivative and the u hat direction of f at the point p naught simply as the gradient of f evaluated at the point p naught, dot product with u hat. See, because that is partial f, partial x at p naught, comma, partial f, partial y at p naught, dotted with ab, which is exactly this. So it's actually pretty easy to calculate the gradient vector field for a function of two variables. Because as I'm going to show you in much more detail next class, partial differentiation is easy. It's easy. Let's do some more while we're at it. So like example 8. Partial derivative with respect to x of like sine of xy squared. What would that go? What would that look like? We'll do these 3 partial derivatives, and that'll be it for today. So the top one, the derivative of sine is cosine. So we do cosine of xy squared, but then the chain rule says we have to multiply by the derivative of the inside function. What's the derivative of xy squared with respect to x? What's that?
Y.
Just y squared, very good. So the y squared, so that just gives us, y squared times the cosine of xy squared. Because we're treating y squared like a constant there. What's the partial derivative with respect to x of x to the y? Y is like a constant, right? Just like n is a constant. What's the derivative of x to the n? Y, yeah, n times x to the n minus 1, right? So this is y times x to the y minus 1. Think d dx of x to the n equals nx to the n minus 1, right? You guys know that. Power rule. What about y to the x? Yeah, natural log, right? Because this is an exponential function with respect to x, like the variables in the exponent. And so, yes, we have to write natural log of y times y to the x. And here we should be thinking d dx of like a to the x. Remember, natural log of a times a to the x is how that differentiation goes. Now there's strings attached to that, isn't there? Y must be what? Yeah, we're assuming y is positive here. Any questions? So we'll do a bunch more of these tomorrow, but I think that's it for today, guys.